Keep learning with BMLabs. Follow for more simple and powerful lessons.
Look at a glacier creeping through a valley. Its movement, the pressure cracking its surface, the rate at which the ice melts, none of these happen in a vacuum. Our physical world operates on multiple, interacting variables at the exact same time. To measure how a complex environment changes, we must isolate those moving parts. We look at how the system behaves when we shift just one dimension, say temperature, while holding another dimension, like pressure, perfectly still. That isolated, highly specific directional rate of change is called a partial derivative. By capturing each of these isolated directional changes and observing how they interact, we can map the true geometry of a multidimensional system. The formal tool mathematicians use to track all these moving parts is the partial differential equation. This diagram outlines a PDE, connecting the independent variables, dependent variable, and partial derivatives into one cohesive statement. Crucially, notice the equal sign. All these geometric components must perfectly balance out to zero. Writing down this rule is straightforward. The true challenge is finding which actual physical surfaces obey this rigorous mathematical law. Let's investigate a specific stripped-down example, uxx minus uyy equals 0. Here, we see what this subscript notation means. Uxx represents how the slope of a surface changes and changes again, measured purely along the horizontal x-axis, and uyy is the exact same measurement, isolated entirely in the orthogonal y direction. When we plug the mathematical shape of a candidate surface into this equation, the result is called the residual. For the shape to be a valid solution, that residual must equal exactly 0, everywhere. If the residual strays from 0 at even a single coordinate, that shape fails the physical law described by the equation. Let's test our first candidate surface, the cubic function, x plus y, quantity cubed. This 3D surface plot maps our function as a sweeping, smooth upward slope. Calculating along the x and y axes, the second derivatives, uxx and uyy, both yield 6 times x plus y. Subtracting these leaves a 0 residual, confirming it satisfies the PDE. Now, let's apply that same verification to a drastically different mathematical shape. This 3D surface plot maps the function sine of x minus y, revealing repeating, rhythmic wave-like ridges. Slicing this surface along the axes, the second derivatives both equal negative sine of x minus y. Subtracting them to find the residual yields 0 once again. Despite its radically different appearance, this undulating wave obeys the exact same universal law as the smooth cubic slope. Here we see the two successful candidate shapes side by side, both visually linked back to our core equation. Visually, they share almost nothing in common. They are completely divergent structures, yet they are governed by identical mathematical rules. This highlights a crucial property of partial differential equations. They are not designed to produce a single, isolated numerical answer. Instead, a PDE defines a family of possible surfaces, a set of geometric possibilities that all share the same internal architecture of change. Which raises a practical question. If a single rule allows for infinite geometric shapes, how do scientists use it to measure one specific real-world phenomenon? We introduce supplementary conditions, initial boundaries, or physical limits that we impose on the math. As this wireframe boundary snaps into place, it aggressively cuts away any mathematical possibility outside our specific criteria. The equation provides the universal law, but it is the highly specific constraints of the real world that filter out the alternative results. Solving a partial differential equation requires combining the grand rules of multidimensional change with the hard limits of our physical reality, snapping one precise, undeniable solution into focus.
Welcome to BMLabs. Learn clearly, think deeply.